So as the introduction stated, I'm Michael Brown. I'm a principal security engineer at Trail of Bits. I'm here to talk about a broad comparative evaluation of software debloating tools that we conducted over the last 18 months, along with our partners at GrammaTech. A couple of my co-authors are here today. Really glad they could make it. Jonathan Dorn and Akshay Sood, so make sure you also pepper them with questions at the end of this talk, just like me. All right, so why do we do this research? So software debloating is an emerging research area that's had a tremendous amount of publication history in the last 7 years. And these tools ultimately aim to achieve some security goals, which is why they're relevant to the community here. These tools are trying to remove unnecessary code from programs to try and improve their performance or improve their security posture. And the large thinking is that if we have less code in these programs, then they have a smaller attack surface, potentially fewer latent vulnerabilities. However, there's a chief problem with the tools that have been published today, in that they all are fairly limited in scope when they evaluate tools. Typically, it's the author of the paper evaluating their tool against one or two other tools that are prevalent in the literature, and also any tools that are performing or that are being evaluated are being done so with an inconsistent set of metrics. So ultimately, it's really hard for users to figure out what tools they should use, which tools are best relative to others in their class, what benefits they should expect, and also which ones are safe and effective. All right, so before we jump into the actual evaluation, let's go do a little bit of background. So there's been over 70 publications in the last 10 years focused on trying to remove bloat in software primarily, but also in software containers, operating systems, or APIs, like their system call ledgers, firmware test cases, you name it. There's been a lot of stuff that's been debloated. Specifically, we're focusing on software debloaters for x86 and x86-64 architectures. So standard disclaimer up front, our findings are limited to these, so please don't try to, or please understand that we're not trying to extend these claims or these findings to anything other than software debloating. All right, software bloat typically falls into two categories. The first is universally unnecessary for everybody. This typically manifests as library code and dynamically linked libraries. So when I write my software, I write my code, but I use code from other people, several different libraries. When I run that code, the entire library is mapped into the address space. So there's a lot of extra code in there that I don't need, that doesn't need to be there. Type 2 bloat is conditionally unnecessary, and that's depending upon the end user's use case. This typically manifests as a consequence of feature bloat. Everyone who's used Microsoft PowerPoint, for example, to make these presentations knows that there's probably 80% of the features that are in that program are features you're never going to use. So various debloaters have been built to try and tackle these two types of bloat. So we've categorized them into 5 categories, and the first 2 tackle primarily this type 1 bloat. The first are called static library debloaters, and essentially these use the call graph of the main program to identify which library functions are unnecessary at runtime, and then remove them or blank them out of the library files. The problem with these types of approaches is that they create fragmented libraries, and you end up with a large number of the same type of libraries, each customized to a main program on your system. And runtime debloaters try to reduce this issue by enforcing policies at runtime about what code should be allowed to be mapped into the address space or what code is reachable from the address space. But this comes at the cost of a significant increase in overhead and complexity. Type 2 debloaters that are primarily trying to get rid of excess features come in 2 varieties. The first is source-to-source. In source-to-source debloaters, the tool will typically analyze the program represented in source code, identify high-level features, map them to the code that implements them, and then allow the user to remove code associated with features. One of the issues is that it requires source code. If we are in a situation where we're dealing with a legacy binary, or we're dealing with closed source software, or dealing with software for which the vendor no longer exists, we oftentimes find ourselves needing to work directly on the binary. So there is another class of debloaters that work very similarly, that work directly on the binary, but the downside is that they require a prior step of disassembly, decompilation, or binary lifting, which come with a high risk of soundness issues, which is one of the things that we evaluate in our study. And finally, there's a class of debloaters that can address either type 1 or type 2 bloat, and they're called compiler-based specializers. These types of debloaters typically ask the user to identify one or more parameters or command line inputs that can be predetermined statically, and then the compiler or then the tool then concretizes those inputs in the code. and uses the compiler essentially as a giant dead code elimination tool to remove code that's going to be unnecessary based on that context. But the disadvantage to these is primarily that they really only perform really aggressive debloating use cases, meaning we've slimmed the program down to operating just a single one of its functions as opposed to one or more. All right, so let's talk about our evaluation, and first how we came up with the tools that that we evaluated. So after doing a literature review, we identified 31 potential tools that we wanted to include in this evaluation. Unfortunately, 7 of them were closed source. We couldn't find access to their source code either on a Git repo or via the author's direct appeal. Of the 24 remaining tools, we found that 7 of them were essentially non-functional. With help from the authors, we were unable to get them up, running, built, you name it. But of the 17 functional tools that we moved forward with, ultimately we found that one of them required a commercial license for Eytchison, so we did not include that one for that reason. And another 6 were not readily adaptable to new targets, meaning that the tools were proofs of concept only. They were essentially hard-coded to the targets in their original studies, and it was a tremendous amount of technical effort to try and adapt them to the benchmarks that we wanted to evaluate. So ultimately, these are the tools that we selected. I'm not going to go through each one and how they work due to time. Please read the paper. There's a lot more information in there, but what we want to take away from here is that we managed to get debloaters from 4 of the 5 categories. The runtime debloaters mostly suffered from being hard-coded or required a significant amount of pre-analysis for their specific targets. So we have 2 source-to-source, 3 binary-to-binary, 3 compiler-based specializers, and 2 static library debloaters that we included in this study. All right, in terms of the metrics that we evaluated them against, like I mentioned before, the debloating literature has over 30 different metrics that are being used. And many of these, particularly for security, are somewhat contested as to whether or not they're valid or useful. Ultimately, we selected these 12 metrics. We can see half of them are performance, related to both the performance of the tool itself and the debloated programs they produce. And then we also selected 4 security and 2 correctness and robustness metrics for the debloated programs that are being produced by these tools. All right, we selected 20 benchmarks, 10 of low complexity, 6 of medium complexity, and 4 of high complexity to evaluate these tools against. We did this primarily because a large number of the tools are, when evaluated by their authors, are evaluated by typically low complexity benchmarks on the order of complexity of bin utils or new utils. So we wanted to see how these tools would adapt to more challenging and higher complexity programs. All right, so let's talk now about how we set up our evaluation. We made 200 attempts to debloat in our study, which is 20 benchmarks times 10 tools. For each combination, we created a debloating specification that was used commonly. It was the same debloating spec used across all of our attempts. We took that debloating specification, combined it with a benchmark program and the appropriate representation that the tool required. We debloated it and produced a debloated program. We then took that debloated program and analyzed it through a battery of functional tests to determine if there were any issues with debloating that broke the program, as well as a differential testing to identify any other new vulnerabilities or new crashing test cases that were introduced into the program as a result of debloating. We also analyzed the program binary itself to take a look at its size and number of linked libraries it was still dependent upon. And then we also did a security analysis using a tool called the gadget set analyzer, which analyzes the code reuse gadgets within a program to determine if debloating has made a exploit writer's job easier or harder by removing or changing the gadgets that are present in the program. All right, so let's get to the results. So how well did the tools perform? The good news is the tools are pretty readily adaptable to the programs that we had in or the benchmark programs we selected. We noted only 15 instances where a tool and benchmark were just incompatible and we couldn't run them. As we expect, the more complex the benchmark program, the more resources the debloater is required to run. But ultimately, with one notable exception, debloating takes less than 20 minutes and takes less than 4 gigabytes of memory on your machine to run. So generally, this is fairly tractable for most users. That said, our exception is source-to-source debloaters based on chisel. They took on the order of hours and days to run, and that's ultimately based on design choices that they made when creating the tool, and not necessarily any issues with our evaluation. All right, so how well did they perform? Let's take a look at success rates. Of our 200 attempts to debloat programs, you'll note that 15 were incompatible. We experienced 41 failures, but ultimately in 144 of the cases, the tool actually completed. It ran to completion and it says it produced a debloated binary. When running against the battery of functional performance tests, we found that 49 of the debloated programs failed one or more of the tests, and 90 of those passed their functional tests. The key differentiator, though, was when we started performing differential analysis, the secondary evaluation on these tools, and unfortunately the results were considerably murkier. And we'll get to those on the next slide. But what I want to show here is that of the tests that did pass, the majority of these are the low complexity benchmarks. Only 21 of the passing debloating attempts were medium or high complexity benchmarks. So when we took a look at the actual debloated programs themselves, we saw mostly stuff that we expected to see. Because we're cutting code from these programs, the static binary size for most of these programs went down. Generally, some tools were better than others at getting rid of bloat. Some tools actually increased the size of the program, and that's due to some design decisions that they make, and ultimately can be adjusted with engineering effort. One thing we did notice that was interesting is that the CPU runtime and peak memory consumption for these for the programs didn't materially change before or after debloating, which kind of goes against some of the performance claims that are being made, and that debloating makes the programs run better or require less memory. In reality, it really is unchanged. But that's also good news because it also means that the tools themselves, we can trust that they are mostly doing what they're supposed to, because we're only supposed to be getting rid of code we don't need. All right, so I alluded earlier that safety was a big issue. We did our differential testing with a novel tool we built called Differ, which is available on GitHub, by the way. So if you recall, we had 90 tests that passed. When running them through differential testing, we found that 25 of them had errors or crashes that weren't detected in the original functional test, and 39 of them failed to remove one or more of the functions that were marked for debloating. Now, that's not necessarily a deal breaker. Debloating is often a best effort type operation, but one potential contributing factor to the soundness of some of these tools is that they simply just didn't make as many cuts as they were intended to by the user. Ultimately, we only found that 26 of our original 200 attempts to debloat actually removed the functionality they were supposed to remove and did not produce an unsound binary. Most of these were for static library debloaters, which are tackling type 1 bloat, which is the simplest version of the problem. We actually found that only 6 cases were able to debloat features successfully from code, which was surprising. And finally, with respect to security posture, we found that debloating has kind of a mixing effect. It stirs up the program in a way that breaks the portability of code reuse exploits, but ultimately debloating did not change or materially impact the kinds of gadgets that are available to exploit writers. Ultimately meaning that debloating did not make it harder or easier necessarily for exploit writers to use the code present in the debloated binary. All right, so we'll wrap up with a couple of key findings. First, software debloaters have relatively low maturity. As we talked about, only 26 of our original 200 attempts made it through to the highest level of fidelity or highest definition of success in our study. The debloaters have soundness issues that are going to require more research and more precise techniques to fix. And then finally, the benefits of debloating are somewhat marginal. Really, we only saw 2 of our 16 metrics where we saw notable or sizable increases, specifically the breaking of portability for exploits and decreasing binary size. All right, once again, final plug, our evaluation data and our tool are available on GitHub. They've been made open source by Trail of Bits. We hope you go out and use them for other studies, or use differential testing or use a differential testing tool in your applications. It doesn't work just for debloating. It really works for finding regression errors of any type of transformed program. So with that, I'm happy to take questions.